Hi everyone, welcome to another video. In this one we'll look at what are the different AWS compute services. Typically, we will touch EC2, serverless computing, Fargate, ECS, EKS, Lambda. Lambda we will go in detail. We will see different phases in Lambda, and we'll, as we always do, we will try to compare the different services in terms of compute like Lambda, ECS, EKS, and we'll also look at something like ASG, EC2, ALB, etc. Right? So let's get started on that. Yes, so EC2, Elastic Compute Cloud. I think most of you would have heard of EC2, one way or the other, because it's one of the most traditional services AWS had, so even before serverless came up, EC2 was always there. Okay, and it is a compute service that runs on virtual machines. That is the first thing. And since it runs on virtual machines, it means it allows you to launch guest OS like Windows in Microsoft, Mac OSs in Mac, and etc. So a single hardware can have multiple VMs, and each VM would have its own guest OS. Okay. So these individual virtual machines will not share the infrastructure OS or the host OS. Host OS would be different, and guest OS, individual guest OS, would be different. Okay, and it is a type of infrastructure as a service. It's a basic building block of your cloud architecture, right? And responsibility wise, you can say it is shared responsibility. AWS would manage the data centers, physical facility, hardware components, the host, and entire virtualization layer, okay, that powers the EC2 service. Okay, you have to manage the guest OS, the individual OSs in each of the different VMs you are having. Okay, the operating system patches, security, access controls, etc. So that is on to you. The host related part is on AWS. Okay, now before we move to other types of compute services, I wanted to also touch upon the difference between VM, micro VM, and containers, because it's very important for us to understand that, for us to get little bit understanding of the hardware behind the different services. Okay, so as I already mentioned, EC2 runs on virtual machines. Virtual machine is more of a heavy setup, you can say. It will have a host OS, hypervisor, virtual machine monitor, and then multiple guest OSs can be there for each of the different VMs running on a single hardware. Okay, so you have a totally separate guest OS in a VM. Okay, there is no shared concept in terms of the guest operating system for each of the applications, for each of the VMs, which may run on a single hardware or host. Okay, with the help of hypervisor, you can have multiple VMs running on a single hardware. Okay, that's why you see hypervisor here. Now moving to micro VM. Okay, let's talk about container first, then we'll come to micro VM. So container, what happens is you have a host OS which is shared. Okay, and there is a container runtime engine there is no separate guest OS concept. Okay, and then directly you have the application. As you can see in the diagram, it shares the host OS. Okay, so each container in uh, each of the different containers powering different applications share the host kernel or the host OS. So that's how it becomes lightweight, right? Now moving towards micro VM, you can say is a combination of virtual machine plus container. We try to basically get the advantages of both in micro VM. Okay, so you have the host OS hypervisor, then instead of a full-fledged guest OS, it would have a minimal guest OS kernel and then the application. Okay, so why did we have micro VMs? Why AWS introduced micro VMs? Containers are fast, but they share the host kernel. Okay, VMs are secure but heavy. Each VM in one hardware would have its own guest OS. Okay, so it's good. It's good in terms of isolation, but it's very heavy. Now, if I have to get the security and the speed both, so VMs would be slow, containers would be fast, VMs would be more secured and isolated. So what we are doing is we are going with the hybrid approach, where we get the container speed and the VM security, which is what micro VMs typically have internally. So they don't have full guest OS isolation. They will have minimal guest OS isolation. Okay, and that's what that's why you have micro VMs. And examples I already mentioned. Containers, you would see container concept in ECS, EKS. Micro VMs, Lambda and Fargate, they are being run on micro VMs, micro virtual machines. VMs, anyway, we know that EC2 runs on virtual machines. Okay, let's move to another very important topic known as serverless computing. So it is an on-demand service and it involves less of server management. So it doesn't mean that you don't have server. Okay, that is the first point I should mention. It just means that you pay only for the usage, that is for the time when the code runs, not for the idle time. Now, problem with EC2 is you also get charged when there is no code running on this on the server, which means nobody is even opening the application, but you have the application hosted on a EC2, you will still get charged because it doesn't matter whether you are using it or not. But that's why serverless computing actually came into picture, that why should there was a question that why should we pay when we are not using the application. So we wanted to move towards more optimized infrastructure. So that's how it came up. So you don't have to launch EC2, upgrade server capacity if incoming load increases, etc. So that happens on the go. That happens automatically, dynamically, and it is known as function as a service. And major AWS serverless compute services would be Lambda and Fargate. Okay, Lambda is a compute service, Fargate is a compute engine. Okay, and these are, as we already saw, powered by micro VMs, which means a combination of VM plus containers with minimal guest OS isolation. So they are fast and also more secure than normal containers, than only containers, and will only run when you invoke it and pay for only the time duration of function execution, as I already mentioned. What are the major AWS serverless services apart from the compute services we just saw? Fargate, Lambda, we already spoke about. You have Event Bridge, AWS Step Functions for service orchestration, SNS, SQS for queuing and notification. You have API Gateway, AWS App Sync. Serverless, what are the different serverless data stores? For static data, you have S3. For dynamic data, you have AWS RDS Aurora for relational database, DynamoDB for as a NoSQL database. Data warehouse, you have Redshift Spectrum, and for ETL, that is extraction, transformation, and load, you have something known as AWS Glue, which is serverless. Analytics, you have Athena and Kinesis. These are the major serverless services we are talking about. There would be more such services. Okay, let's move towards the container services we just mentioned. So you have ECS, EKS, Fargate, and ECR. Yes, so let's talk about ECS first. It's a containerized orchestration service which supports Docker containers. Okay. You can install, operate, scale your cluster management infrastructure in AWS, and they are defined in a task definition, okay, which you can use to run ECS tasks or groups together as a service. ECS tasks can be run using EC2 or Fargate. So Fargate and EC2 are engines. These are container services. Okay. EKS is Kubernetes service. Containers here are grouped into what is known as pods. These are the basic operational units in Kubernetes. And again, these pods can be run using EC2 or Fargate. They are cloud agnostic and allows you to move workloads to your on-premise or Azure, GCP, etc. So Kubernetes is an open source service, you can say. It's not an AWS native service. Okay. Now, what is AWS Fargate? It's a serverless compute engine. Okay. This is the major difference between Farless and EC2. They work on both ECS and EKS. They allow you to build apps without worrying about provisioning, scaling, management, etc. Okay, that is all done under the hood, and it is the most cost effective than containers running on EC2. Okay. Now, what is ECR? ECR is a fully managed Docker containerized service. It stores, manages, and deploys Docker container images. It's like a registry where you store and manage the Docker container images. Okay, the different Docker container applications you are having, those containers you can basically store as image. Okay, for like taking a snapshot at a particular time, that image you want to store. Okay, for your later use. Integrated with Amazon ECS and stores your Docker images in highly scalable and available architecture. Okay, a very important concept, how EC2 is different from Fargate. We already saw Fargate is a serverless compute engine. Now let's understand the architecture here. You have container orchestration, which happens via ECS or EKS. Okay, so these are container orchestration services. And who are the compute engines we are having? EC2 and Fargate. And your application runs on the containers. Now ECS, EKS, they are used for task scheduling, service scaling, load balancing, health checks, etc. Okay, ECS, EKS, they don't run by themselves. They need containers. How ECS, EKS run containers? First option is on EC2. Okay, so in that case you manage the EC2 guest OS sizing, AMIs, patching, etc. The second option is ECS, EKS on Fargate. Now Fargate would be serverless and AWS managed, and it is good for bursty load. Okay, Fargate is a serverless compute engine for containers. You manage containers but not servers. Okay, vis-a-vis EC2, where you have to manage the servers. Okay, now what are the serverless architecture types? Static single page apps, you can use S3 plus CloudFront. For service oriented architecture, you have EKS, ECS on EC2, EKS ECS on Fargate plus Lambda plus DynamoDB. Okay. So basically ECS EKS on EC2 is now changing or moving towards ECS EKS on Fargate with Lambda and DynamoDB, like the total serverless stack. Okay, so older applications which were running on EC2 are now moving towards ECS EKS on Fargate and not on EC2. Okay, let's now move towards AWS Lambda. Okay, so we will discuss this in detail. It's a serverless compute engine service. Okay, so we have seen traditionally with EC2 you have to manage the servers. Here, no servers to manage. You deploy the code and you run. You get you are being billed only for the time the code runs. Okay, Lambda will do the heavy lifting of managing and scaling. It supports various languages: Java, Node, Python, etc. Obviously it is lesser, the cost is lesser than EC2. Okay, now you have to choose the memory while setting up the Lambda. It will auto select the other configuration parameters like network band, with CPU processing power, disk IO, access to RAM, etc. And if you have higher memory, then the execution time decreases and makes it faster, right? Let's look at how you can invoke Lambda. Now there are two ways in which you can do the invoke Lambda. One is the synchronous way. The request goes to Lambda, wait for it to execute, then response return. Okay, so you have the client, you have the get order, let's say, is the endpoint, and you will have the API gateway, then Lambda, which will then fetch the order from DynamoDB, and response gets back, is returned back to the client. So this is all synchronous. Everything happens in a single in sequence, and response is returned at the same time. In asynchronous execution, what happens is, let's say you have a put order API. It will go, the call will go to the API gateway. There will be an internal event queue. It invokes Lambda, and as it invokes Lambda, you will immediately get a return status 202, not 200. Okay, that is a major difference. What 202 means is that it just specifies that the request is taken. There is no response body. It is not the actual response. The response is still to come. The processing in the DB has not yet been completed. And on the client you can have a loader which tracks the status of the completion of the order. As and when status becomes complete, or the return status becomes 200, the loader can go away and you can show the response. Okay, that's how asynchronous execution is maintained or managed in the UI, and it is good for operations that don't need to wait and return a response there and then. Okay, for example, long latency operations like batch operations, order processing, video encryption, etc. So these operations require longer time to entirely process. Okay, so you can't have them as a synchronous invocation. Okay, because then the entire workflow will take a long time, and the user would need to wait on the screen for a longer time. The loader keeps on showing. Instead, what happens in Amazon when you are placing an order on Amazon, it says order placed successfully. It doesn't mean that the order processing was complete. There again, it would be an asynchronous mechanism, I assume, where it is at the back end it is giving back a 202 status code, and then the entire order processing queue or the different steps would get started. and maybe it takes a minute or two to entirely process the order. Okay, but user is not waiting for 1 or 2 minutes. He directly sees order placed once he clicks on the pay button, right? Okay, a Lambda execution. So there are 3 phases of Lambda execution: init phase, invoke phase, and the shutdown phase. Okay, init phase is occurs when Lambda is invoked for the first time after a long period of inactivity, right? And it creates execution environment in micro VM. Execution environment is nothing but it comprises CPU, RAM with amount depending on memory settings configured. Lambda services will download the function code and run the initialization code. The AWS stores code in S3 in encrypted form. So now what is initialization code? It comprises library downloads, dependency imports, initialization of variables, DB connection, etc. The time it takes to bootstrap execution environment is called cold start. Now you have to basically do the background processes, correct, for you to actually execute the code. So you need the dependency imports being there, you need the initialization of variables, the type library downloads. That is the meaning of initialization. And time and the total time it takes to bootstrap the execution environment, that is making the execution environment ready for execution, is known as cold start. Generally you don't pay for the cold start if the initialization time, meaning the time it takes to do whatever we talked about, is greater than 10 seconds, then you pay for the entire time. Otherwise, if it is lesser than 10 seconds, then AWS doesn't charge you for the cold start. Okay, so to avoid the cold start being greater than 10 seconds, you have to minimize the dependency imports. So the optimization of the dependencies involved, which will basically get included in the cold start time, you have to make sure or try to make it as minimum as possible, lesser than 10 seconds, so that you are not charged for the entire time of the cold start. Okay, so you have to put only those dependencies which are actually needed. So so there we need to be careful. Okay, moving to the other one, that is the invoke phase. The Lambda function handler is executed in this phase. This is the most important thing. The actual code is run in this phase. So init phase is all about initializing the environment, that is the cold start. Execution phase is about, invoke phase is about the execution of your actual code. Execution environment context reuse. Now there is this concept. So it is, what is this concept about? It is about reducing the resources that were initialized during the phase, like DB connection, library, global variables, etc. right? So Lambda keeps the execution environment intact for a period of time after the first call. Okay, so the execution environment just like that doesn't go away, it keeps the execution environment intact. Your execution environment has a predefined storage of 512 MB and for a /tmp directory to store and cache the files at the time of function execution. So you can make use of this directory to store any temporary files which you require at the time of execution, and predefined storage given is 512 MB. Reusing the initial resources will help lower the total execution time and save doing initialization again. And the execution context is temporary, avoid storing state data in it. Okay, so execution context, which is about DB connection, libraries, global variables. So you have to avoid storing data, which state data which you need to retain. Okay, because that context is temporary. Okay, moving to the shutdown phase. Shutdown phase is basically AWS terminates the execution environment after a period of inactivity. I think this is wrong somehow. AWS, this should be execution. I don't know how it, okay, and this should be AWS. Okay, so AWS will terminate the execution environment after a period of inactivity, typically 5 to 10 seconds. If the function invocation stops, then this can happen. So if the function is no longer getting executed, it will wait for 5 minutes and then the execution environment would be terminated. So the initialized resources are wiped out. Okay, the context reuse won't happen. So it all depends on the idle time. If there is a period of inactivity of greater than, let's say, 10 minutes, then this will happen, the shutdown will happen. Okay, what are the Lambda layers? So you use Lambda layers to store external dependencies that will be used by multiple functions. Now you can optimize the dependency imports where multiple functions use the same dependency imports, and you are not unnecessarily having external dependencies getting stored or getting created for each and every new function. So what you can do is you can use Lambda layers to store the external dependencies, and external dependencies are deployed to Lambda layers as zip files. Okay, what are the advantages? They are shareable, dependencies are shareable. Lambda layers reduce size of dependency and size of all functions. So imagine each function you are not having a separate dependency layer or external dependencies zip file. Instead you have a common zip file containing the different shared dependencies, and plus each function can have its own separate dependencies also, but whatever could be shared are put in the external dependencies Lambda layers so that it can be used by multiple functions. So use Lambda layers to store the external dependencies which would be used by multiple functions, which can be used by multiple functions. That is a good design. So it helps in separation of concern. Business logic independence are separate. Okay, okay, now what is concurrency in Lambda? Provisioned concurrency keeps Lambda pre-warmed and it eliminates cold starts. What is reserved concurrency? It is predictable plus low latency, limits maximum execution, does not prevent cold starts. Okay, so this is how provisioned concurrency and reserved concurrency are different from each other. Reserved concurrency would have predictable and low latency, but it will not prevent cold starts. Okay, so let's say you have consumers in SQS. Anything that calls receive message on the queue, example, multiple Lambda invocations could be there, and there could be multiple EC2 or multiple ECS, multiple pods, right? So the consumers are different, the code is the same. So you have SQS queue which is designed for horizontal scaling. That's the idea. Now what is the concurrency here? Let's talk about that. Consumer A polls SQS, gets message M. SQS makes M invisible for visibility timeout to say 30 seconds. So while invisible, other consumers can't see it. Okay, so idea is that if this queue SQS has 1000 messages and batch size is 10, so Lambda can scale up to 100 concurrent executions, which means 100 concurrent Lambdas can be executed at the same time if required, right? Because if batch size is 10 and 1000 messages are coming, each Lambda takes 10 messages at a time. So you can have 100 Lambdas processing those 1000 images, and if a Lambda receives 10 messages in a batch, fails on message 7, then the entire batch is retried Okay, all 10 reappear after visibility timeout. Now what is visibility timeout? It is basically the time frame for which the specific message gets invisible for the other consumers once it reaches a particular consumer. Okay, because you don't want to have duplicate processing, you want to dedupe the duplicate you want to have dedupe in place. So one message being processed by a single resource to avoid redundancy, right? And if, let's say, consumer A fails to process that message and the visibility timeout expires, then M appears again in the queue, which and then it can be processed by any other consumer. Okay, that's the idea. Now even after maximum retries, if the message is not getting processed, the message will go to dead letter queue, and it will not reappear in the queue, because the failed messages shouldn't block processing. It shouldn't be that a message keeps on failing. Keeps on failing and then keeps on reappearing. So after a few retries, it goes to DLQ, where it will then not reappear for processing. The other messages which will anyway continue in their queue. Okay, so if one more thing is if partial batch response is not enabled, and if a message in the batch of 10, let's say message 7 fails, then the entire batch is retried. Okay, so if you don't want to try the entire batch, then you have to enable what is known as a partial batch response. Okay. Okay, at Lambda versus ECS versus EKS, we wanted to also compare the different compute services for us to know where the particular compute services is best used for, where it is not. So Lambda, feature wise, we know it is serverless, event driven, auto scalable, pay per execution, and it is stateless, right? And it is best for event driven workloads, short running tasks. Please remember, short running tasks, unpredictable traffic, you would want to use Lambda. Spiky traffic, where you don't have a stable traffic, more spiky traffic, and for low usage you want to optimize the costs. Okay, example use cases could be API backend, image processing, stream processing, scheduled jobs, etc. So event driven, unpredictable traffic, spiky traffic, short running tasks. Okay, the tasks which do not take longer time, and it is not ideal for long running jobs greater than 15 minutes and all, right? Heavy CPU memory control needed, stateful workloads, workloads which require persistent connection, legacy monolithic apps, all those it is not very much ideal for, because it's a serverless application. It's a recent or a new service as compared to EC2. ECS, now containers without Kubernetes complexity. Okay, AWS managed container orchestration is there. We already saw it has two modes, EC2 launch and Fargate launch. It is best for microservices architecture, AWS native orchestration and controlled scaling, right? And use cases could be batch jobs, REST services, background workers. It is not ideal for Kubernetes ecosystem, multi-cloud portability. So the ECS is not cloud agnostic. Any custom orchestration logic, heavy custom orchestration, if it involves that one, then it becomes difficult for ECS to handle. For such scenarios, you should go for EKS. If you need multi-cloud portability, cloud you want something to be cloud agnostic, which can work in GCP, Azure or AWS, then you should go for EKS. Okay, so it is best for portability, as we already just spoke. Large enterprises, complex microservices architecture, EKS is best. Hybrid or multi-cloud, it is not ideal for simple applications, minimal operations. Okay, so if it is a simplistic architecture, don't go for EKS. Okay, EC2 ASG ALB application load balancer, network load balancer. This is one of the concepts we, this would be the last concept before we wind this particular tutorial on compute services in AWS. Now, EC2 must span multiple availability zones for the entire thing to be highly available, right? AZ, as we already spoke in another previous videos, should have separate power, separate network, separate failure domain. So if suppose if all EC2s are in one availability zone and power is out, then the entire application is down. You don't want that. You want fault isolation, okay, failure tolerance, fault tolerance. So that is why EC2s generally must span multiple availability zones. And what is load balancer? Health check instances stops sending traffic to unhealthy EC2s, okay, it routes traffic to only healthy ones. There are two types, ALB and NLB. ALB is HTTP based, REST APIs, path based routing. NLB is TCP UDP, for ultra low latency, millions of connections, you would go for NLB. And ASG is auto scaling group. Load balancers, they would distribute traffic but does not create new servers, okay, but ASGs can add or remove EC2 instances when load increases, drops, and it replaces failed EC2 instances, okay. So ALB with ASG and EC2 instances and running in multiple AZs is a highly common high availability pattern in AWS, okay. So if you have a EC2 stack, you want to make it highly available and less and less management headache, then you should go for ALB, which is the application load balancer plus auto scaling group on EC2 instances deployed in multiple AZs, okay. So internet to ALB to ASG, EC2 in private. ALB would be in public subnet, EC2 would be in private subnet with the ASG enabled, that is auto scaling group enabled, which would add or remove the EC2 instances depending on the load, okay. So this makes the management little easier of EC2 instances. So ultimately LB or load balancer, that handles traffic. ASG makes it scalable, handles capacity, minimizing operations, and AZs helps in fault tolerance, as we just spoke, okay. So I will stop here. Hope this particular video was informative. We tried to cover the AWS compute services in the best way possible, easiest way possible. We have, the notes are created in such a way that they are easy to comprehend, easy to take down, easy to remember, okay. And we are talking about the impactful points in all of these services. Please go ahead and register for the AWS and AI Builder community we are building, and try to leverage the advantage, like-minded peers. Link is there in the description. Go ahead and register for it, and we'll see you inside of the community. So till the next video, this is Romit signing off. I'll see you in the next one. Thank you.